converging lenses, optical instruments like cameras, projectors, microscopes, binoculars, telescopes, etc., have drastically widened our view of the world. Eyeglasses allow millions of people to read and see in comfort. Have you ever wondered which optical component makes all this possible? It is simply a lens. A lens is a piece of a transparent material bound by two surfaces of which at least one is curved. A lens bound by two spherical surfaces, bulging outwards, is called a biconvex, or simply a convex lens. It is thicker in the middle than near the edges. A lens bound by two spherical surfaces, curved inwards, is called a biconcave, or simply a concave lens. It is thinner in the middle than at the edges. Let us understand certain terms related to these lenses. The central point of a lens is called its optical center. It is usually represented by the letter O. For these lenses, convex or concave, each surface forms a part of a sphere. The straight line passing through the optical center and the centers of these spheres is called the principal axis of the lens. Principal axis is perpendicular to the surfaces of the lens. The effective diameter of a spherical lens is called its aperture. It determines the amount of light that passes through the lens. Here, we shall confine our discussion to thin lenses whose aperture is much less than its radius of curvature. Let us understand the basics of refraction of light through a convex lens. A convex lens may be thought of as an arrangement of a number of portions of triangular prisms with a very small glass slab at the center. The base of each prism points towards the principal axis of the lens. We know that a ray of light incident on a prism bends towards its base and then emerges out. Now, let us see what happens when a beam of light parallel to the principal axis strikes the lens. We can see that these rays undergo refraction as they enter the lens and leave it. First, they bend towards the base of the respective prisms, and then emerge bending towards the principal axis. Thus, after refraction through the lens, they converge to a point on the principal axis on the other side of the lens. This point is called the focal point or principal focus of the lens, and is usually denoted by F. Here, the refracted rays actually meet at the focus. Hence, a convex lens is said to have a real focus. Because a convex lens converges the light rays that are incident on it, it is called a converging lens. We can see that the bending of rays is maximum at the top and bottom prisms, and it reduces as we move towards the principal axis. This is because the top and bottom prisms have the greatest angle between the refracting surfaces. As we move towards the principal axis, this angle reduces. This causes corresponding decrease in bending of the rays. At the center, no bending occurs for the glass faces are parallel. The ray through the optical center emerges undeviated along its original direction. A single piece of glass that curves outward and converges the light incident on it is called a convex lens. The distance from the optical center to the focal point is called the focal length of the lens and is represented by F. According to the sign convention, the focal length of the convex lens is positive. Thicker lenses having greater curvature bend the light more and thus have shorter focal length. Hence, thicker convex lenses have more converging power. Let us see what happens if the parallel beams incident on the lens are inclined to the principal axis. After refraction through the convex lens, they converge to certain points in a plane containing the focal point. The plane passing through all such points, perpendicular to the principal axis, is called the focal plane of the lens. What if light rays parallel to the principal axis are incident on this lens from the other side? This lens has the same effect on light incident from the other side. Therefore, a convex lens has two focal points, usually represented by f1 and f2, one on each side, equidistant from the optical center. According to the principle of reversibility of light, a ray of light passing through the focal point of the convex lens emerges on the other side of the lens parallel to its principal axis. Having understood the action of convex lenses on various rays of light, let us now see how they form images. For different positions of the object, a convex lens forms images of varying sizes and nature at different locations. These lenses are therefore used in instruments like cameras, telescopes, etc., to form images that we see with our eye, which itself has a lens. Summary. A lens is a piece of a refracting medium bound by two surfaces, at least one of which is curved. A convex lens is thicker in the middle than at the edges. A lens may be thought of as an arrangement of a set of tiny prisms with a very small glass slab at the center. The focal point of a convex lens is the point on its principal axis where the light rays incident parallel to the axis converge after refraction through the lens. The distance from the optical center to the focal point is called the focal length, f, of the lens, and is positive for a convex lens. A convex lens is a converging lens and has two real foci.